Howdy, in this video we will have an introduction to multiple existential and universal quantifiers. The first thing to consider is basic predicate logic, and we can think about that on the square of opposition. In traditional logic we would call this an A statement, this an E statement, this an I statement, and this an O statement. But in any case, here we have all A's are B's, here we have no A's are B's, here we have some A's are B's, and here we have some A's are not B's. There's only one quantified variable, namely x. But recall that relations are possible with constants and variables. If we have multiple variables, we need multiple quantifiers. So here's some basic hints when we're dealing with multiple quantifiers. The first thing is to break down the problem into its variable parts. Second is to figure out the quantifications. You have different variable parts. What is the quantification to those respective parts? And then think about the relation. And then think about translation. Put things together. So here's an example. And in this example, we're making a simplified assumption, namely that the domain is restricted to people. If we have the proposition, everyone is loved by someone or other, let's first break down the problem into its variable parts. So we have everyone is loved, and we have someone or other. Those are two variable parts. On the one hand, you have something that's universal, and then you have something that's particular or existential. We have a relation. We have LXY. In other words, X loves Y. But the question is, in what quantified way? We're told that everyone is loved by someone or other. Hence, on the one hand, we have something that's universally quantified, and on the other hand, we have something that's existentially quantified. We have for all X, or excuse me, for all Y, there is some X or other that loves Y. So we'll translate this as for all Y, there exists some X, LXY. Notice that on the one hand you have that universal quantifier, on the other hand you have this existential quantifier. The relation is X loves Y. Notice the order, X loves Y. It doesn't say Y loves X. And now we have this for all Y that is being loved by some X. X is doing the loving and Y is being loved. And as we noted, we have, again, the universal quantifier with Y and the existential quantifier with X. As I noted, we're making a simplified assumption here. We're going to pretend everyone or everybody is the same thing as everything. Otherwise, we would have to set up a conditional that restricts, so to speak, the antecedent to people. We would have to specify that explicitly. But here, we're going to restrict the domain to people, so we're all right. Let's think of another example. Here we have everyone loves someone or other. We have two variable parts. Everyone loves someone or other. On the one hand, we have something that's universal, and then we have something that's existential. We have a relation. X loves Y. The question is, in what quantified way? For all X, there is some Y that loves X. And so we get for all X, for some Y, LXY. We first have something that's universal, then we have something that's particular or existential. And it turns out that all X loves some Y. Example 3, someone loves everyone. We have someone loves everyone. So this time we have something particular or existential to start with, and then we have something that is universal. We have a relation Lxy. There is some x that loves all y, because after all, someone loves everyone. Hence we get there exists some x such that for all y, Lxy. Again, we start out with something that's particular or existential. Then we have something that's universal. It happens to be that there is some x, some existing x, at least some x, that loves all y. How about someone loves itself, or something loves itself? So we have something loves itself. We just have something that is particular or existential. The relation is a little different because here we just have x loves x. So Lxx. So there is some x that loves x, i.e. itself. Thus we get there exists some x Lxx. Example 5, someone loves someone or other. We have two quantified variables. We have someone loves someone or other. Both happen to be particular or existential. We have the relation Lxy, x loves y. In particular, we have there is some x that loves some y. Someone loves someone or other. So there is some x that loves some y. Put this together, we have there exists some x, there exists some y, Lxy. Example 6 tells us someone is loved by someone or other. It's very similar to example 5, but it's a little different in that in example 5 we have someone loves. Example 6 we have someone is loved. We have someone is loved, someone or other. Both are particular or existential. Lxy. But note, here we have there is a y that is loved by some x. Whereas before we had some x loves some y. But here we have y is being loved by some x. Put this together, we have there is some y, there is some x, Lxy. The order is important. Here we have there is some y, there is some x. Previously we had there is some x, there is some y. Based on the fact that, for example, 6, we're told that there is some y that is loved by some x. Whereas before we're told that there is some x that loves some y. Order is very important. Example 7, everyone loves everyone. Everyone loves everyone. Two quantified variables, both happen to be universal. The relation Lxy, for every x, loves every y. Hence we have for all x, for all y, Lxy. Example 8, everyone is loved by everyone. It's very similar to example 6. Just like example 7 is very similar to example 5 in terms of loving or being loved. Okay, so here we have everyone loves. Here we have being loved. Everyone is loved by everybody. Anyways, we have everyone is loved by everybody. Both happen to be universal in scope. We have the relation Lxy. For every y, it is loved by every x. So every y is loved by every x. Hence we have for all y, for all x, Lxy. So every y is loved by every x. Before we had every x loves every y. So the ordering here is different. All right, example 9, there is someone who is loved by everyone. We have there is someone who's loved by everyone. Two quantified variables. The first one happens to be particular or existential, and the other universal. The relation LXY. There is a y that is loved by every x. There's a y that is loved by every x. Hence we have there is a sum y such that for all x, LXY. Not too bad, but it does take a little practice. Number one, it says all men love science. Love is a relational predicate. We have two general classes of things, men and science. Thus we need two quantified variables. We're told that all men love science. Thus we have a universal affirmative proposition. If we think about the square of opposition, and because it's a universal affirmative proposition, it'll be a conditional. And in the antecedent, so to speak, we will announce our variables x and y, and the consequent will have the relation. So we'll have for all x, for all y, brackets, parentheses, mx, and sy, arrow, lxy. So for all x, for all y, if x is a man and y is science, then x loves y. Number two, some philosophers love mathematics. Love is a relational predicate. We have two general classes of things, philosophers and mathematics. Hence, there are two quantified variables. We have this sum. Hence, we have a particular affirmative proposition. But also, and maybe I should write this explicitly, let's say some philosophers love all of mathematics. So we have two quantified variables. One is existential and the other is universal. We can think about it this way. There exists some x such that, now here we're going to have a conjunction because we have a particular proposition. So we'll say px, x is a philosopher, and now we're going to say the universal portion. So we need another quantified variable for all y. So we'll say if y is mathematics, then lxy. There exists some x such that x is a philosopher, and for all y, if y is mathematics, then x loves y. And that makes sense, doesn't it? Because on the one hand, so we have this and statement, we have a particular proposition. But on the other hand, embedded within that, so to speak, we have that loves all of mathematics. So here we have our conditional. Number three, every employee is under some employer. Under is a relational predicate. We have two general terms, employee, employer. And I'm going to say that employee is W and employer is E. Also notice the every. So this is a universal affirmative proposition, but embedded within that is this sum. So we have a quantified variable that's particular. We have a quantified variable that's universal. So we'll write for all x. What is the antecedent? Well, that x is an employee. So we'll say wx arrow. And now comes our existential quantifier. There's this sum y. That y is an employer and u xy. That x is under y. Hence we have for all x, if x is an employee, then there exists some y such that Y is an employer, and X is under Y. Number 4, there's a philosopher who teaches anyone who's attentive or curious. Teaches is a relational predicate. When we say there is, this means we have an existential quantifier. And when we say anyone, here we have a universal quantifier. Hence we'll say there exists some X such that X is a philosopher, and this philosopher will teach anyone who is attentive or curious. So we have now our universal quantifier for all Y. And we'll say in the antecedent we have to announce our variable, so to speak, which is Y. So we have AY and attentive, or, so we have an or, curious. So Y is attentive or Y is curious, then TXY. There is some X such that X is a philosopher, and for all Y, if Y is attentive or Y is curious, then X teaches Y. Number 5, some but not all philosophers are empiricists or rationalists. Notice that we have some, so we have a particular sentence, and we're also having this all, but it's being denied. So we should really treat this as a conjunction, and one of its conjuncts, so to speak, will be denied. In other words, we can say that there exists some X such that X is a philosopher, and, parentheses, X is an empiricist, or X is a rationalist, and it is not the case that for all Y, if Y is a philosopher, then Y is an empiricist, or Y is a rationalist. On the one hand, we said there's some philosophers who are either empiricists or rationalists, but not all. So I just added, and it is not the case that all of them are. And that captures the essence of that sentence. Number 6, some humans eat vegetables, but not animals. All right, here we have 3 quantified variables because we have 3 general classes of things: humans, vegetables, animals. Notice that we have some humans eat vegetables, then we have this but not animals. Okay, so some humans eat vegetables, but not animals. All right, so there exists some X such that, okay, so we need 2 more variables, Y and Z, and we'll treat them as universal. So we'll say for all Y, for all Z. Overall, we have a particular sentence. So we have a conjunction. So we'll say X is a human, and now we have a conditional. So in the antecedent, we have to announce our variables. We have to say that Y is a vegetable, that Z is an animal. So we'll say VY and AZ arrow We have this eat, and eat, of course, is a relational predicate. So we'll say E x y, x eats y, and it is not the case that E x z. Notice that here we have x eats y, and it's not the case that x eats z. Of course, z is for animals. It's being related to animals, right? And y is to vegetables. So there exists some x such that for all y, for all z, x is a human, and if y is a vegetable and z is an animal, then x eats y, and it's not the case that x eats z. Enough of that. Let's get into some argumentation. We'll do 3 here. The first one is premise, someone loves everyone. Conclusion, therefore, if there is someone who loves Anna. Intuitively, this is obviously valid. Anna belongs to the class of everyone, and someone loves everyone, so it must be the case that someone loves Anna. But we want to prove this with first-order predicate logic. We'll first symbolize, so let's do that. Our first premise, our only premise, is there exists some x such that for all y, Lxy. And our conclusion is, therefore, there is someone who loves Anna. So there exists some x such that Lxa. With most of these proofs, we're going to be dealing with the reductio ad absurdum, or the indirect proof. In other words, we're going to assume the contradictory of this conclusion. We're going to prove that that leads to a contradiction, and because of that, we can then conclude that conclusion does in fact follow from our premise. For line 2, let's assume then it is not the case that there exists some x Lxa. This is just an assumption. And because it's an assumption, we'll place it under quarantine. We can't instantiate that. We can't work with that because there is this negation sign in front of a quantifier. We want to remove that, so we're going to have to use a change of quantifier rule. The way I like to think about this is through the square of opposition. So here we have, if we just think about there exists an x such that Lxa, this is a particular affirmative proposition that would exist right here in the square of opposition. So there exists an x such that x is an f. That's the general form. And that is contradictive to a negative universal sentence. For all x, x is not an f. Because we are denying this particular affirmative sentence, we could affirm the negative universal. Hence, for line 3, we can get for all x, it is not the case that Lxa. So change of quantifier rule with line 2. Let's work on line 1. We have there exists an x such that for all y, Lxy, we can do existential instantiation. So for line 4, and we can only instantiate, so to speak, one variable at a time. Okay, so now we're dealing with existential instantiation. So we'll be left with for all y, and now we will instantiate our variable, excuse me, a variable x, and we will choose b. So we'll say for all y, Lby. This is existential instantiation, line 1. And now we can do our universal instantiation, where we will instantiate Anna. So we'll say for line 5, we'll say Lba by the universal instantiation of line 4. And now let's work on line 3 and universally instantiate that. So for line 6, we'll substitute b for x, so we'll say not LBA by the universal instantiation of line 3. Now notice lines 5 and 6 contradict each other. So for line 7, we'll say LBA and not LBA by the conjunctive rule, line 5, line 6. And then from that, because we have a contradiction, for 8, we can deny our assumption. We say that assumption cannot be the case. So we'll say not there exists some x such that LXA by our indirect proof with lines 2 to 7. And then for line 9, we can use double negation to get there exists some x such that LXA by double negation of line 8. So therefore, the conclusion follows. For argument number 2, there are two premises. In this case, we'll do another reductio ad absurdum proof, which is also called an indirect proof. Hence, we will contradict the conclusion we wish to prove. For line 3, we can then say it is not the case that for all x, there exists some y such that LXY. And this is an assumption placed under quarantine. We don't want a negation sign in front of a quantifier, so we'll do a change of quantifier rule. For line 4, from line 3, we can get there exists some x such that it is not the case that there exists some y such that LXY. For line 5, we can do an existential instantiation. So we'll say it is not the case that there exists some y, and we'll substitute a for x, so LAY. Existential instantiation, line 4. However, once again, we have that negation in front of a quantifier. So for line 6, we'll do a change of quantifier rule. For all y, it is not the case, LAY. Let's instantiate line 2. For 7, we can get there exists a y such that UAY. So we substitute a in there. This is the universal instantiation, line 2. Now we can do another instantiation, this time an existential instantiation on line 7. Hence for 8, we can get UAB by the existential instantiation of line 7. We substituted b for y. For 9, we'll do a universal instantiation of line 6 to get not LAB. We substitute b in there for y. And now I think we should work with our first premise. So for 10, we can get for all y, UAY, arrow, LAY, by the universal instantiation of line 1. And then, because we have to move step by step, we'll do another instantiation, but this time for the variable y. For 11, we can then get UAB, arrow, LAB, by the universal instantiation of line 10. Notice lines 8 and 11. We can do a modus ponens inference. So for 12, we can get LAB, modus ponens, 8 and 11. And now note that 12 has LAB, but 9 has a contradictory of that, not LAB. Hence for 13, we'll say not LAB and LAB, conjunction of lines 9 and 12. We have a contradiction. Hence, outside of quarantine, the assumption must be incorrect, so it is not the case. That is not the case. For all x, there exists some y such that Lxy, by our indirect proof with lines 3 to 13, and then for line 15, it therefore follows, for all x, there exists some y such that Lxy by the double negation of line 14. For argument number 3, we're told that everyone has a person who is his mother. Mother is definitely the relational predicate. We have a universal affirmative proposition with everyone, but embedded within that universal affirmative proposition, we have an existential quantifier with a person. Hence, for line 1, we have for all x, if x is a person, then there exists some y such that y is a person and y is the mother of x. So for all x, if x is a person, then there exists some y such that y is a person and y is the mother of x. For line 2, we have anyone who is the mother of his mother. This is grandma. Grandma is a relational predicate. Mother is a relational predicate. Moreover, we have a universal affirmative proposition overall. We have this any1. Here, there are 3 variables. We have this any1, this any person, we have mother, we have grandma. Hence, we need for all x, for all y, for all z. So for premise 2, we have for all x, for all y, for all z. This is a little tricky. We just have to think about the relations between these variables, between x, y, and z. Overall, again, there's a universal affirmative proposition, hence we have a conditional. And the antecedent, so to speak, always announces the variables. The consequent will be about this relation with grandma. So, for premise 2, for all x, for all y, for all z, what's in the antecedent? We will need y is the mother of x. So m yx and z is the mother of y. So m zy arrow g zx. So we have y is the mother of x and z is the mother of y, implies that z will be the grandma of x. Conclusion, therefore, everyone has a grandma. Once again, we have a universal affirmative proposition, but embedded within that, we have an existential quantifier. So therefore, for all x, if x is a person, then there exists some y such that y is the grandma of x. Notice that the conclusion, we have this conditional here. In this case, the proof is pretty long because we have all these relations. And the best way to start this one, I think, is really just to assume this antecedent and work from there. For line 3, we'll say px, and that's just an assumption under quarantine. And now we can work with line 1 and do a universal instantiation. So line 4, we can get px arrow, there exists some y, such that py and myx by the universal instantiation of line 1. Line 3, we have px that appears in line 4 in the antecedent. So for 5, we can get there exists some y such that py and myx by modus ponens with lines 3 and 4. For line 6, we can instantiate line 5, so we'll get pw, so w for y, and mwx by the existential instantiation of line 5. For line 7, we can get pw by the simplification of line 6. Just keep on working with this. If we move into a dead end, that's all right. We'll just see our error and backtrack if needed. So we're going to, as one professor one time said, we're not necessarily going to fail it, but we're going to frail it. Whatever happens, happens. Just try and see what happens. For 8, we'll get mwx and pw, commutative rule, line 6. For 9, we can get mwx by the simplification of 8. Here I'm going to, again, work on line 1 once again, because we're going to need to get some more out of that. So let's, for number 10, do some instantiation once again. So we'll get px arrow, there exists some y, such that py, and so p, no, what am I saying p for? Okay, so be m, y, w. And we'll have to substitute w for x. And then we can do that modus ponens inference again with that assumption from line 3. So for 11, we can get there exists some y such that py and myw modus ponens 3, 10. And then we want to instantiate that. So for 12, we just had to run through these variables. We had to run with that variable w. So for 12, we'll now run with the variable, with z, right? So it would have to be z. So we'll get pz and mzw by the existential instantiation of line 11. And then for 13, we get pz by simplification 12. For 14, we can get mzw and pz commutative rule line 12. And so for 15, we'll simplify, get mzw simplification 14. And let's do some combining here with lines 9 and 15. So for 16, mwx and mzw, conjunction of 9 and 15. Now it's about time to work with line 2, premise 2. We're going to do some instantiation, so we'll have for all y, for all z, m, y, x, and m, z, y, arrow. Oh, sometimes my stylus goes. Okay, g, z, x. All right, so this is universal instantiation, line 2. For 18, we're going to do another universal instantiation. So now we'll have for all z, p, no, what am I saying p for? M, there we go, m, wx. So we'll substitute w in, so w, x, because we are working with that variable y. So w is substitute for y. So m, wx, and m, zw, arrow, gz, x. All right. So this is universal instantiation 17. For 19, once again, another universal instantiation. So we'll have MWX and MZW, arrow, GZX, universal instantiation 18. So with our variables in place, and line 16, we have MWX and MZW. We can do a modus ponens inference. Hence for 20, we can get GZX, modus ponens, 16, 19. And now with this, with this variable z, we can generalize. Okay, it's an existential generalization, not a universal. But for 21, we can get there exists some y such that gyx, but the existential generalization of 20, and hence this is the consequent we want based on our assumption. And that assumption is the antecedent, so outside of quarantine for 22, we can say px arrow, there exists some y such that gyx, by our conditional proof with lines 3 through 21. Now in this case, x is really a general variable. So we can do a universal generalization. Hence for 23, we can say therefore it does follow for all x, px arrow, there exists some y, gyx, by the universal generalization 22. That's it for this video. Up next is a so-called bonus video. The topic is invalidity in predicate logic. I'll see you soon.